Okay, so welcome back. So first thing I'd like to remind you about the final presentation discussion. So we have 7 groups. You should already engage discussion within your group. Sort of the outline of the presentation will be needed for the homework that's due this coming Sunday. And today I'm going to finish week 10's topic, mostly finishing the tomographic tools. Then I'll begin week 11's topics. It's on quantum Fourier transform, quantum phase estimation, and other applications. Yeah, so we mentioned the importance of tomographic tool because you need to know the proper functioning of your elements, such as state preparation, gate operation, and at the end of measurement. And I already introduced the first one on state tomography, and then I think I started discussing process tomography. But let me basically review some of those from the last lecture. But the last one is on the detector tomography. I already mentioned this in the error mitigation in the topic on quantum error correction, but I'll emphasize that again later. So the idea of quantum state tomography is that there's an unknown state prepared by some source, and you are allowed to make measurement on that. And there are a few copies of the identical states. So by enough statistics, you should be able to figure out what the state is. So I gave you an example of 1 qubit, and it's convenient to write it in terms of the poly basis. The reason is that these coefficients, when they are uniquely determined, that specify the state completely. So up to the statistical fluctuation, but these coefficients, they are really measurement from the 3 different axes. So 0, 1 is this direction, north and south pole, and the plus and minus 1 that give you the Rx, which is in this direction. So basically that's measuring the probability of getting a plus minus the probability of getting minus. So Y is the corresponding measurement in this axis. Okay. Yeah, so once you have information about these components, then the state is determined. And that can be easily generalized to multiple qubit states. In the 2 qubit case, you would expand the state in terms of product of poly matrices, including identity. Okay. So the measurement would be in some sense the measuring coincidence, like I detecting maybe the plus state here and there's a 0 state, so you need to combine all different combination of bases. So, and it's not going to scale very well if you have many qubits, so it'll be exponential. So we talk about measuring the state, but the next tool, quantum process tomography, is to determine a process or a black box which is doing something to the state you send in. So you have a row send in and row prime send out. By measuring the row prime, you're trying to figure out the process. So we write a general quantum operation in terms of these cross decomposition that we mentioned earlier. So this is useful to debug some quantum gates, but the gate would be limited to maybe 1 or 2 qubit gate, or only a few gates. So the idea is to see by sending different way of states and you measure this in tomography, you figure out what this bug is doing. Okay, so that's the idea. But in more detail, there are 3 different ways. I think this is where I discussed last night. So it's quite easy to understand. So in terms of matrix, right? So if, for example, a qubit, you have a 2 by 2 matrix, and you see how it transforms, right? So this is exactly what you want. But if we know how does each component transform, then we basically know everything. So you're asking how this component 0, 0, 0, 1, and 1, 0, so 0, 0, 0, 1, 1, 0, 1, 1. How does each component transform under this black box? Okay. And because even though 0, 1 is not a state, right? It's a component, but it can be decomposed into a projector into plus state, plus I state, 0 state, 1 state. So basically, these are measurement. These projectors representing measurement in those spaces. So these two off-diagonal terms can be measured using 3 different combinations of measurement. Okay, so from this we know that we only need to have 4 different input. So 0, plus, and plus I, and 1. So these are the 4 states that you send in, and you know how they transform. Then you will know how the combination of these 4 components transform. Then you figure out any 1 qubit transform. Okay, so that's the idea of standard tomography, process tomography. Any questions? This is what we talked about last time. Okay. I am actually going to prepare in homework 7, which is optional, but there will be an example on this process tomography. Okay. So this is one of the 3 approaches. The second is the so-called entanglement assisted process tomography. So previously we have to send 4 different states, right, for 1 qubit. So we could also ask, could we just send 1 state or just one, the same state? We always prepare the same state. We don't need to change. The answer is it is possible. You just send in a Bell state, so 0, 0, 1, 1. So we could expand this Bell state in terms of also the poly basis. So it's basically this combination. Okay. So if the box is experienced by the first qubit, so maybe 1 qubit goes to here, you're trying to figure out what this black box is doing. Yes.
Yes, the black box is unitary, or we
can. It's not unitary, but assuming it's any valid quantum operation. And
so will the box be random?
So it would have some action like this.
Yeah.
Remember we talked about this when we're talking about the error of there's an environment and there is a global unitary because of interaction, and at the end the environment was measured. So, and you were seeing the action when you trace out the environment and the system is like this.
And they can have a different year for a different time. We just get
no, we assume the same. I mean, it's sort of fixed operation. This is the operation. This E is the operation that define the black box in general. It could be just a unitary. It's also possible.
But if the box has some entanglement with the environment, it will have a different outcome each time we send the same qubit.
So you have to assume, yeah, the black box should be reset. Yeah.
Okay.
If you saturate the action of the black box or has some time dependent, then you are measuring some average action. So you're averaging.
Yeah.
You are just detecting the average action over a period of time. Okay. And we're assuming that the change is small. So you can.
Okay.
Yeah. Okay. Yeah, that's also an important question because maybe the environment of a quantum computer will also change over time, and which actually happened. So, for example, IBM, they would need to calibrate the machine from time to time. Okay, but the point here is, suppose let's ignore these complications, just asking about characterizing a quantum action, quantum operation, which you don't know, right? But by sending, we were saying we could send in 0, 1, plus a, plus I, right? But we could also send just one bell state with one of the qubit going through this, okay? And you can easily understand that the action, right? Because the qubit 1 is going through that. So let me just denote it as E acting on the identity and E acting on sigma X and E acting on sigma Y and E acting on sigma Z, right? And because the I, sigma X, sigma Y, sigma Z, they are really independent. So by measuring the joint 2-qubit state of how the output is through the black box by one of the qubit, you know what basically phi has become maybe 2-qubit state. You know how this transformation, so this is by measuring. This is by tomography. Then from here, you infer the black box. Okay. So that's the idea. That means you can do that. In fact, okay, let me erase this. My explanation here may be a bit abstract because I'm just saying that these I, sigma X, sigma Y, sigma Z on the second qubit sort of are independent. So whatever you do on the first, you could by just separating the action into these different independent matrix, you would be able to know the action. But actually, it's probably easier to understand in terms of the so-called remote state preparation. So maybe you remember that when we talk about remote state preparation, so there's Alice and Bob, they share this entangled state, 0, 0, plus 1, 1. So remote state preparation is, for example, Alice measure in the 0, 1 basis, then Bob would get 0, 1, right? Alice could measure in plus and minus basis. Bob would also get something like that. So Alice measure in plus and minus I think there might be a change in this. The plus I outcome on Alice would corresponding to minus I outcome on Bob. So in some sense, I'm measuring. So let me just say Alice is here, Bob. Right, Alice and Bob would perform measurement. In fact, for this problem, Alice and Bob, there's just one group. But if you want to, using the idea of remote state preparation, you can think of Alice, the measurement of Alice here is preparing a state for Bob, right? So if Alice measure and get 0, so that means the state that's just coming out of this before the black box is 0. So then you know how the zero get transformed. And if Alice measure get plus, she prepared Bob's state to be plus, and Bob is measuring how the plus state is transformed, right? So in some sense, using this remote state preparation, we can reduce the understanding of this entanglement assisted process tomography to just what we learned in this, right? By Alice's measurement, she prepared Bob's state into one of the 6 states. And we only need 4 to be able to get to characterize the black box, right? Okay, does that make sense? By Alice measuring here, she is preparing different combination of Bob's initial state that goes through the black box. Of course, they need to be working together. To Alice need to tell Bob what measurement outcome she has, right? But treating this as one observer, then they can do whatever they want. They can exchange their classical information. Okay, does that make sense?
Quick question.
Okay, I hope that does.
Okay.
Yes.
So quick question.
Can you speak louder?
Yes. So if there is noise on Alice's side, if there's noise on
Yeah, that would also be
well,
get imprinted to Bob's side.
Okay.
Yeah.
Do we
So here
have
we
any...
would assume the measurement is precise, but then you could also incorporate the noise into the, and then maybe the process would determine up to certain error. Yeah.
Okay. Thank you.
Yeah. But this is the same as if Bob's state preparation has some noise.
Okay. So we could move the...
Yeah.
Thank you.
So this is using entanglement because we see that these are the Bell state. But you could actually ask the question, is entanglement really necessary? Can I say send some unentangled state? So we have seen example of unentangled state, right? So I could just mix the Bell state. I think this was in your homework. You're asking about the entanglement of this. We could send something like that, right? Okay. So could we actually use this state for the process tomography? It turns out that we could use this even in the regime where it is not entangled. So remember when this R is less than 1/3, it's not entangled, right? So yeah, so this is what I wrote here. And in fact, comparing to the Bell state, it's just changing the weight of the corresponding term, right? So we still have the first one is how the identity get transformed. The second one, how poly sigma X get transformed. Third one, poly sigma Y get transformed. The fourth one, poly sigma Z get transformed, right? If you can infer how these 4 operators get transformed, you will be able to know how any arbitrary 1 qubit state get transformed. Yeah. But you see that this number is smaller than the case of a case of Bell state, right? This is overall 1/4, but the coefficient is 1 here. It's overall 1/4, but there's a smaller 1/3 here. So in some sense, this part is sort of overall white noise, and due to this has a bigger ratio than the other 3. You would expect that you need to have more data to perform that process tomography using such an unentangled state. Okay. Yeah. But I think the key is if you can understand the first one, it's conceptually the same as the second one if you introduce the remote state preparation picture. Okay. Yeah, this has been tested experimentally in few experiments. Okay, so the setup, okay, the process is here. Fortunately, that was the process was on the lower arm than what I drew earlier. Okay, but you can imagine the measurement here is preparing the state here. Okay, so there are some measurement outcome. For example, if this is identity, this is the standard one. Identity should just, these are the points, the 3 points on the block sphere. So the X, Y, and Z. So identity will remain the same. This is called a wave play. So it's like a rotation. So we rotate the 3 dots. Yeah, so you can see using the 3 different ones, they all get similar result, except for example, this one has a probably larger error. There's also some thing you could introduce to change to act as if you have an environment. This is called decoherence. You see that we mentioned something like a deploying channel. This will be similar. So it's changing the block sphere, right? It's shrinking the block sphere. And you see that if I use the entanglement assisted one, we all get really consistent result. Except this one. So somehow the analysis from the experiment indicate that the block sphere somehow blow up to be greater than 1. So this is actually not physical. This is related to the question by Wayne Han that the way the coherence is induced is actually using the same degree of freedom as we generate the so-called Werner state in this sphere. So this state. And so you are recycling the degree of freedom that used to generate the state, so that actually would induce non-physical action. Yeah. So that's somehow a limitation of the process tomography. Okay. Any question? Yeah. So in order to have this form, as Wenhan pointed out, if you are using the same degree of freedom that prepares the state, then the process tomography, that picture, or if the environment changed with time, then you probably will get something that's not consistent. Okay, in this case, we're using the same degree of freedom to create the Werner state. This row 1/3 state. And then we use that to let it go through a process which induce decoherence by using the same degree of freedom. Yeah, and somehow that you may intend to decohere the state, but it can end up actually annulling the effect that you use to create a Werner state. Okay, but this is just yeah, some extra caution that one need to be aware. Okay. Yeah, so detector tomography is a subject that we've seen before. We want to send a well-characterized state, but in this case, the detector is unknown. Detector action is unknown or to be determined. Yeah, this was a notion introduced quite early. So the question is, by sending different states for the detector to detect, and by registering different clicks, can I infer what actually is the detector doing? So in some sense, this is a reverse process of the state tomography, right? In the state tomography, we assume the states are known, but detection, the projection is perfect. And here is the other case. Okay, so it was introduced in around 2000, and a few years later, people use this to characterize the photon detector. But yeah, so but we're going to focus on qubit. This can actually be used to carry out on IBM machines. So we already introduced the system transmod qubit. So I don't want to go through the detail of this discussion, but you see some snapshot of the machines at IBM. For example, there's qubit here, there are 5 qubit, and they are linked by some resonators. Here are more qubit, is IBM Q 16 Melbourne. I think initially it was created to have 16 qubit, 2 qubit, I think were not very good. So remove that to be 14 qubit. I think recently 1 qubit sort of has a good quality, so that currently it's 15 qubits. So the idea is to sense, so we could sense 6 different states, very similar to what we encountered before in the process tomography. Okay, so these 6 states can be easily created. The 0 state was already initialized when you call a quantum register. 1, you just flip by x. Plus, you create it by using Hadamard. Minus is the transformation of 1 by Hadamard. And these plus and minus I, you use phase gate. So these are the 6 states. So it turns out you could, by sending these and then analyze what the detector is doing. So we would write more generally that when the detector click and say, I'm measuring 0, or detector click and say, I'm measure 1, we can use 2 operator to denote their actions. And as you can expect that these 2, let me go to the next slide. These 2 operator, in the ideal case, is a projection for the pi 0 to be projected to the North Pole. One case is to project to the South Pole and has this this expression. So we can sort of characterize them using expansion of these Pauli matrices. Yeah. So there's one slide that I skipped, is basically telling you that if I send in state row M and I characterize and detector L click, I denote by operator pi L. According to the quantum theory, this is just probability, just the trace row of the state and the measurement operator. And this basically is a measurement data. The number of time an input state M such that the detector L click. And so this is from the experiment. So I should say this is from the experiment. And here is slightly more technical part is one use the so-called maximally likelihood function that can iteratively find this operator pi L. So I don't want to go into the detail, but the formula just to show you that there's a way to do some iteration. You start some guess to begin with, and then you can find the experimental data, you can find this operator R, so you can iterate to get the guess of pi L, and then you sort of iterate the process. This is really just processing the experimental measured data. Yeah, so I put a star to indicate that this is slightly technical, but you can program in, for example, in Python code and gather the data from IBM, and you can process that. And this is, in fact, what we did. For example, I show a 5-qubit here. This representing the detector of detector operator for the 5-qubit. Yeah, so you can see they are not perfect, right? They don't point all the way to the north or south pole, indicating that there's some loss of the accuracy here. Okay. Yeah. So the top row and the bottom row, the difference is that the top row we characterize each qubit detector individually, and the bottom 5 qubits are characterized altogether in parallel because these are simple state preparation and measurement. Okay. So then you can ask, what can you do if you know how the detector works?
The
Right,
probability is trace pi rho.
Yeah. So remember the probability. So if let's say a projector P0, right, and you have a state rho, the probability of getting 0 is this, right?
Yeah.
Yeah, but we generate the detector, detection to some operator ML. So this PL would be trace rho ML. Okay.
So can yet model all kinds of error.
Model all kinds of error. This is basically just telling you what the measurement operator is. So from this, we get what it's supposed to be, and then you can ask, is this pi 0, how close is it to the projector 0? So the difference of that is the error, right? It's the error of the detection. It's not going to be perfect. Okay, so, but once we characterize the function of the detection, we can actually use to mitigate imperfect measurement. So that's what I mentioned earlier in the quantum error detection. Okay, so yeah, so here's some math derivation, but it's not that crucial, assuming it's pointing mostly to in the z-axis, right? So only the third component and the identity. So we only keep the zeros, identity, and the third component. We can write, so this is the measurement. Suppose you have n qubit, and you measure the outcome could be 0, 1 for the zeros qubit, and 0, 1, etc. for the rest, the n qubit. And so this denotes the measurement outcome. This is the measured. And here you can write in terms of a probability distribution, this is ideal. Because I really just write trace rho with some perfect projectors, but then there is a coefficient. Okay, and you can really write at the end, this is the measured probability is related to the ideal, this is what you want, and with some matrix, right? So by knowing this M, you could invert the equation to extract the P ideal probability distribution. And this M is obtained by the detector characterization. Okay, so yeah, so the upshot is that you can invert and then get an ideal distribution. Okay. Any question? It's maybe a bit technical here, but the point is that this is what we measured. This is what we want. And this is something we already measured. We know how the detector function. So we can sort of correct its error.
I think that is not invertible. We can only invert the rotational part.
So this is a matrix. It can be inverted. So P.
Yeah, but if inversion maybe exceed 1.
Yeah,
And
so that's that is that's a good point. So of course you need to constrain that this P need to be, sorry, the other way around. So P M is this, yeah. The ideal should not be negative. Okay, so it can happen that the matrix is such that there is when you do the inversion, you get some negative number. Okay, but there are ways to do that, so you can minimize the difference. Minimize the difference of, you calculate one and the m so that this is minimized. Okay. Or you can invert and just truncate. So there's some example here.
Yeah.
So this is really the simplest fail state creation. The only action is on these last 2 qubits. And the ideal case would be these two probability distribution. This one and this one should be 50%. So the labeling of the IBM qubit is, this is 0th qubit first. This is the 4th qubit. So this is 0th, 1st, and 4th qubit. And this is the actual measurement distribution. And what you could do is you could invert P with constraint that this is greater than 0. Okay. And if you do that, you find that the two main one actually the number increases and the other one actually decreases for the ideal, so the extracted ideal case. So another way you could do that is maybe you don't impose a constraint. If you invert and you get the ideal probability distribution to have negative number, you just set that to 0 and renormalize. That would also be close to this. Okay, so that's just one applications. So that's, you can also find IBM that they have similar implementation, but what they do, for example, in the 3 qubit case is they prepare all computational basis state. These all 8 of these states. So let's say they prepare 0, 0, and they measure all the 3 qubit also in the same basis to see what is the probability of getting 0, 0, 3, 0, 2, 0, and 1, etc. And then they complete this table. It's very similar to our matrix M. And they also have function to apply the inverse to mitigate error. Okay, so that has now become the standard. Okay, but the idea is similar. So they only measure the computational basis here, but somehow the way we're doing here, we get more information about how the detector is working, like how the error is pointing, and more detail of these coefficients. Okay. So I want to mention that this tomographic tool has a disadvantage that the number of bases need to scale exponentially with the number of qubits. Right? For example, to complete this table, n qubit, there are 2 to the n, right? So there will be 2 to the n on this side, to the n on that side. So this matrix is 2 to the n by 2 to the n. So that's too many. Yeah. So it's still a active research question, how to reduce these, so to make these tomographic tool more scalable. There's one particular tool called randomized benchmarking. In a sense, it's related to the process tomography, but the goal is not to characterize all the gates, but to get some average error for some groups of gates. Okay, so this is used to characterize, for example, 1 qubit error, 2 qubit error, or CNOT gate error, etc. The other tool that, or matrix that introduced by the IBM group is the so-called quantum bottom. It basically quantifies the overall quality of quantum circuits. It's also an average quantity. I don't think I have time for the moment to discuss these in more detail, but if there's still time close to the end of the semester, I come back and maybe also do some case demo. But if I cannot and have no time, you can, I'll give you reference so that you can go back and go to these references and check out for yourself. Okay. So that's the end of this tomographic tool. Any question before I move on to this week's topic? Okay, if not, let me switch to it. Okay, let me first save the slides. Let me see. I should have this open. Okay. Yeah, so this week is about quantum Fourier transform and phase estimation. And this is the basic algorithm that can be used for factoring, solving quantum linear system. So let me just remind you, you have seen probably Fourier transform, which is a function, and then there's a exponential 2 pi x times k. So this, if you're a physicist, x is the real space, and k is a momentum or wave number space. And there's also an inverse transformation, basically just divided by minus I, minus here in the exponent. This is for the continued case. And for discrete case, if we only have n points, we can do a discrete Fourier transform. Instead of integration, this will be a sum. And this exponential will be e to the I 2 pi k times x over n. And in this case, k and x, they are both integers. So this will be integer as well. Okay. And there's also its inverse transformation. So I'm sure many of you have seen this. It's very useful in physics, mathematics, engineering, etc. But if we want to talk about quantum, we could expect what we want is we take j, which is in some sense x. We want to go to a k, but in this particular form, right, you expect you will have this. And we representing the right-hand side in terms of quantum state. So basically, it's really just this, putting a k and summing over that. So I should say, should be, you would expect a x and then summing over this. Okay, that's just what you would expect. maybe a quantum computer could implement this. Okay. So in fact, this can be turned into a quantum circuit. So J here, I'm going to use the binary representation, J1, J2 up to Jn. I would also write as K1, K2 up to Kn. Okay, so that's the top line. And the n here, we would also write in terms of 2 to the n, and small n is the number of qubits. Okay, so that's the formula. Okay, and here is the quantum circuit that implement that. So let's just look at the structure. J1, J2 up to Jn, and you want to transform to this, and it turns out this actually can be understood as a n-qubit state, product state, also transform into a n-qubit product state like that. So it's maybe not obvious, this particular form. Let me just make it bigger. Yeah, so these JNs, so okay, so there's some notation here. Let me just make it smaller. So this point J1 ... Jn is really just a binary representation. It's really J1 over 2, J2 over 2 to the 2, etc. Jn over 2 to the n. So this is really binary representation. Okay. There's some derivation that you can find the detail also in the textbook Nielsen and Tron, but let me sketch that. If you don't get the detail, maybe it's not that big issue, because whatever you need to know is the input and the output form. So, but let me go through this derivation anyway. So I'm going to write J. This is binary representation. Depending on the convention, J1 is the most significant digit. So I have to write J to be J1. J1 has the weight 2 to the n minus 1. So I'm writing J in terms of this summation. Okay, I hope that this is clear. And also I'm going to write K in a similar form. Okay. Okay, so the K is going to be KR. These are the component raised to 2 to the n minus R. Yeah. This is the convention that's used, but other paper may, let me just say, other paper or book may use K equal to Kn, Kn minus 1. So be aware of the convention. Okay. Okay, so I'm going to do this derivation. So bear with me. So first, we're going to write J in terms of this form and K in terms of that form. So you have J sub Q raised to the n minus Q, K R to the n minus R, and you sum over all these Q and R. Okay. You can do it qubit by qubit. So we're going to order the qubit and combining the one related to the rth K in terms of this I 2 pi sum over the still the same and JQKR. And I'm going to just cancel out one factor of 2 to the n. So for example, I'm canceling out this. Okay, so it's still the same expression, but I'm just separating into individual qubits. So now it is expanding individual one. The K is binary, so it could be when KR is 0, that's just the 0 state, and everything here has a factor of 0, so it's identity 1. For the one that KR is 1, so you just put this to be 1. So you're left with JQ, and Q sum over from 1 to n, but because of this factor, if n minus q minus r is greater than 0 or equal, then that means it's integer. Integer times 2 pi is just give you a phase 1, factor 1. So we might as well just starting from this. Okay, so this is really detailed derivation, but I think what comes out is more important is the end result. So here I'm just writing in terms of the binary. Yeah, this binary representation. But to write it out, so just write it out. The first one, when r equal to 1, this is starting from Jn, and just 1 Jn. When r equal to 2, you have Jn minus 1 Jn. When the last qubit, you have all the bits from here. Okay, so that's the derivation. So that's why this is the final form. This is the final form. Okay, compare these to that. Okay. So it's very interesting that this Jn is get put it here, and then Jn also here, but it's the next digit when you include Jn minus 1. Let me make it bigger. So it's easy to read this, even if you don't understand the detail. So you have the last qubit has all the phases, digit J1 up to Jn, and you can think of this one is a shift of this to the left. But because J1, if you shift it to integer here, it has no contribution because e to the 2 pi I times integer will give you 1. You can imagine you shift more digit until you have the last digit J here. So I hope the structure is clear. Maybe I pause here to see if you have question. Okay, so if not, this is the next slide, just rewriting things. Yeah. Now we can maybe go to the circuit a little bit. Okay. So we see this is the design outcome, but somehow the circuit, when we write this way, is sort of reverse. So let's just look at the output here. It's really just the swap of the reverse order. The one that has all the digits is on the first qubit. The one that has just the last qubit is here. So there is a swap that perhaps need to be implemented to reverse order. This is the mathematical derivation. But this is the way that circuit implement. And you see up to the reverse order, we can get this. So let's just look at this part. This one has a Jn here. So in order to get Jn, you just do a Hadamard transformation, right? So Hadamard, I hope you remember the Hadamard transformation. Get put a minus sign here if the bit is 1. Okay. So this we can achieve. So I'm explaining the detail of the circuit. So to get this, you just do a Hadamard transformation. But you see that all the qubit above have the digit Jn, right, before the swap swapping the order. So
What
it's a
is 0? What is 2 pi I j?
Oh.
0.
So do you know 0.1, right?
Oh, I get the idea.
Right, but in the binary digit, this will be, okay, you don't write 0, but it's, okay. But if it's 1.1, then this is 1 over 1. But this one has no contribution because 2 pi I times 1 is 1. Okay, let's come back to here. So you see the structure that this Jn appear everywhere on this side, right? But the digit is slightly different. So this gets shifted 1 digit. So you need to do a control unitary, right? If Jn is 1, then I shift that, I add a phase. I add a phase to that with appropriate digit. R2 is a matrix like this. It only has action, non-trivial action if the state is 1. So R2 is e to the 2 pi divided by 2 to the k. So 2 is meaning shift to the 2 digit to the right, right? So it's here. And now you see the structure. This would have control unitary to that, shifting 2. And this one, the one above this line would have 1 shifted 3, so have R3. And then this one shifted n digit to the right. And this one will shift n digit to the right. This is n minus 1, this is n, okay? So, and if you see the Jn minus 1, that can be obtained just by the Hadamard transformation. But this Jn would minus 1 would also appear above. So you will see that there are many control gates from this n minus 1 qubit to all the qubit above, but with appropriate shift of the digit. Okay, does that make sense? And then until the J2, there is a control gate that shift the digit. Okay, and this first one start with the Hadamard gate. So that's the structure. Okay, any question? Okay, but I think, how do I? Okay, I think the importance of that is, this is sort of the position, right? Or the computational basis, these J1, J2, Jn is mapped to the phase information. The phase is such that one of the qubit has all the digit. Then you have n minus 1 digit, and you have 1 digit here. Okay, so that's the structure. This is called quantum Fourier transform because it's doing this J goes to a momentum space picture like that. Okay, so I hope that I explained the circuit well enough so you understand the Hadamard. Right? The Hadamard is put in a superposition so that you can accept the phase. It's like the phase kickback from somewhere. Okay, and the control phase gate, because these, depending on the value of for example here Jn, J1, okay, J2 here depends on the J2 here, so that's the control phase gate. And the swap is because somehow the way we derive, this is the first qubit. We might sort of reverse, we could sort of do the reverse, and then we may get the reverse. So that's a convention. So there are swaps, right? So, but these swap, you don't need to do it at the last step, but you could do it along the way. So I drew this. It's not easy for me to draw this, but you could sort of do the Hadamard and then control, and then you swap. So the crossing here represents just the swap, physical swap. Maybe this line just go here. J2 would have a Hadamard, right? So this Hadamard is here. And you do this this way. In the end, you need to sort of swap back. Yeah, so you can see the J1, if you follow this line, it goes down and J1's here, J2 go up and it comes down. And sort of like a pinball goes up and it hit the wall and then bounce back. And now it's appearing at the third location from the bottom, etc. So they are the same circuit, but I explicitly do the swap along the way. Okay. Yeah. So what is the usefulness of the quantum Fourier transform? So it can be easily seen that the circuit we have here is really special in a sense that we are sort of converting the bit information to the phase encoding here. So this means that if we have a phase information is particular form, if we reverse the circuit, so reverse, what I mean is you do the Hadamard and you do the control phase gate to its conjugate, and then you follow by Hadamard and do the conjugate of this, etc. At the end, you read out the phase, right? If this is the phase encoded in this structure, you read out the phase. And so that's what is shown here. So this is the quantum Fourier transform. If suppose I have a way to encode the phase in terms of this structure, right? So I want the first one has the last bit. So this means that I need to shift the phase. So in this case, shift to the so you need to do this gate raised to 2 to the t minus 1 power. That would multiply 2 to the t minus 1 to the phase here. So assuming U is an eigenstate of a unitary operator, which has a phase e to the 4 pi phi, if you do this only once, that just put a phase into here. So that's very similar to this here. If you do it U square, you put 2 times the phase in this here, very similar to that. That's shifting the digit to the left and removing the integer one, right? So you do this. So suppose this phase phi is exactly t bits. Then I can read out this t bit by reversing the circuit. So doing the inverse of quantum Fourier transform, I can extract the phase. If the phase exactly t bits, t is the number of qubit here that I use to encode the phase. If this is exact t bit, then I can obtain the exact phase description here. So J1 here obtained will be the phi 1 and etc. JT here will be the phi t. Okay. This is assuming that the phase is exactly represented by t bits. If not, then we need to use more bit qubit, right? So you can see that the accuracy would depending on how many first register qubit you use, right? Okay. And therefore, if the phase is not exactly represented by these t bits, then there will be an error in getting the measurement outcome. Okay. So I'm giving you an example. So suppose I have a phase like this. Okay. Suppose this phase divided by 2 pi is this number. And in terms of binary, this. Suppose I am only using 4 qubit to represent the phase information, to extract the phase information. 2 to the 4 times this is 1.1, etc. like this. So you can see that the best probable outcome would be, in terms of here, would be, you can see the distribution. The two best outcome will be these two dots, right? So this one, integrated one here, is this representation. That has a probability of about 30%. The other one, this one, 2 here, has the probability of 48, 49, almost 49%. So they are the closest. So if you, but you see the information, they are correct up to the first two, 0, 0, 0, 0. The third bit may be an error here, right? Comparing, so let me just highlight it. This will be J1, remember, or phi 1, phi 2, phi 3, right? The first two, in terms of the 4-bit, these two are accurate, okay? But there might be other places where you would have error even in the second bit. So you see that if phi is not exactly represented in terms of t bit, then there will be error. Okay, but these errors are not huge. Okay. Okay, so yeah, I'm not going into the detail of analysis, but let me just say how you could do, right? So you have the phase encoding. Remember the circuit that we have from last page. You apply the U and U raised to 2 to the 10 power. They give you this phase state. And then you do the inverse Fourier transform. This is minus sign comes from. Really doing the inverse transform, you get this state. And you ask what is the probability of getting an encoding J. So that's what I'm plotting here. I'm plotting the coefficient absolute value square as a function of these J here. Okay. Okay, by analyzing this, you will see that, so I'm not going through the derivation. You can see the detail from the textbook. So if you have t qubit or t bit to representing the phase, there can be error. And if epsilon is the error probability, because the quantum mechanics measurement, if phi is not exactly represented, there will be an error. Suppose the error is epsilon, or the success probability is 1 minus epsilon or greater, then if you have t bits, it's only going to be accurate to t minus this small amount of bits. Okay, so meaning the accuracy will be reduced by this amount. So in order to get, if you want to get a t bit accuracy, you need to supply t plus this much qubit. Okay. So and you see this structure of getting the phase encoded is sort of, you can, if you're a physicist and you like to think this used as an evolution in time, there's a t here. This is like a conditional evolution. So if I have time equal to 0, I don't apply. Actually, I would, yeah. So, and then if I have time equal to 1, then I would apply u once. And up to I have t to the 2 to the minus 1, I apply this many gates. But in terms of that is an evolution in longer time. Okay. This picture will be useful when we talk about solving the linear system. Okay, any question on this? So this page is talk about the accuracy. Okay. If there's no question, I want to mention as comments that if the quantum Fourier transform of its inverse is the last step, then you don't really need to use the control phase gates. They could be replaced by measurement and followed by the classical control. So for example, if you're doing the reverse inverse quantum Fourier transform, you're trying to measure the J1, J bit. Then you will do the Hadamard and read out to see if it's J0 or 1. If it's 0, then you don't apply anything. If it's 1, you apply a R2 to the second qubit. Then you apply the Hadamard and then do the measurement. So you continue to this, and this means that you don't need to do a quantum control. You only need to do a classical control. You only apply this phase gate when the bit readout is 1. So this is called a semi-classical quantum Fourier transform, or its inverse. And this picture also leads to the so-called iterative quantum phase estimation, meaning that you only need to have one Ancilla qubit. So let me just go back. Here we need to have T qubits. You only need to have one, but you need to each time have to refresh to 0. So in a sense, once we read out, this is the one that's apply some phase to okay, this is the one that raised to the most significant power. And once you read this, you can undo this here. You can cancel out this. And then that's what's meaning here. You undo that. And then you can apply Hadamard and read out. Then once you have that, you refresh a new one, apply the Hadamard, encode the phase. And so it's really a sequential way of implementing this. Okay, but I'm just only mention these as comments. These are the further study if you want. Any question? Okay, so let's see how much time. We still have 7 minutes, but maybe let me give you a really simple example. So if we want to measure the phase of Sk, so if its eigenstate 0, this is e to the 2 pi 0 times 0, but s applying to 1 is e to the 2 pi times 1 over 4, right? So the phi here is 0. Phi here is 1 over 4, so that's 0.01. Okay. So what I'm doing here is I'm applying, this is control S gate, and this is control S gate square, but S square is Z, so I'm really doing the control Z here. So this is just control Z. So in some sense, this is encoding a phase 2 pi phi times 2. This is e to the 2 pi phi times 1. Okay. So then I can read out. Yeah.
Hadamard gate at qubit 2.
This is just encoding phase.
Yeah, I mean, if you want to phase kick back, you should put a Hadamard gate at O2.
So this particular case, phi is 0, right? Phi here is 0, so this really is a plus. This is also really a plus. So here I'm doing the inverse of the R2. So let me just go back to the circuit. I'm doing the inverse of this to read out. Does that make sense? So maybe just point out the structure. This is encode the phase. This is inverse quantum Fourier transform. I'm reading out the bits here. In this particular case, should be 0, 0. Does that make sense? So this here is a result that I obtained from some long time ago from the machine, which I don't think is in service. But at that time, I actually measured all the 3 qubit. So you can ignore the first bit. Right? So you get, this is an actual run. And the 0, 0 is the correct answer, but has only probability about 55. This is an actual run on real machine. Okay. In the case of 1, you can read out, but the phase, as I said, is 0.01. So there's a 0, 1 here. So this case, you see that this is the correct. This is the correct one. So you should ignore the third bit. For this circuit, I did not actually measure this is the newer circuit that I updated today, but this is the old measurement. Okay. So this part is the same, almost the same, except that this is state preparation. I prepare a 1 here, right? And these I prepare plus, plus. Then this part is always the same. Inverse quantum Fourier transform and measurement. Okay. So maybe I can go to the notebook.
Can I have a look
Yeah.
for the state preparation slide?
No, no. I mean
Previous
saying
slide about phase estimation. There are some U square.
U square. Yeah. This is U, control U, and this is control U square. Yeah. So I already simplified that. This is control S, and this is control S square. Control S square is.
Oh, yeah, the phase is 0. I get the idea. Thank you.
No, this is okay. This particular is the phase 0, but the next one would have these 1/4, right?
So you put different U, they have a different phase.
No, same U. I always put U is S. I always put the same. This is
Oh,
S.
I mean input state.
Input state is to get the eigenstate, right?
Yeah, different eigenstate.
Yeah, different eigenstate extract different eigenvalue. Okay, so let's see. Okay, I'm doing the share. Can you see the notebook?
Yes.
Okay, so here I define a 3-qubit register, quantum register, and 2 classical bits. So I'm preparing plus for qubit 0 and 1. So let me just say here. And then also, if I don't do anything, the last qubit is also prepared in 0. So it's picking the eigenstate that has just phase 0. Okay. But to get the phase, I do a control unitary. This is they are doing the phase kickback, control S. unfortunately, there's no control S, but control S is control U1. U1 is the, if you put the angle to be pi over 2, then that's the S gate. So the control S gate controlled by qubit 1 and acting on qubit 2. So that's this one. And then I do a control S square, but S square is control Z. So I just do control Z from qubit 0 to qubit 2. That's the end of phase encoding. So I put a barrier, and this is doing the inverse quantum Fourier transform. And I've taken care of the sort of the swap. I don't care about the swap. I just know which qubit, which bit I should read. So I just apply the Hadamard, right, the reverse, and apply the control R2 here, and then the Hadamard. Right? Then I should do the measurement, and then I append the measurement here. So, and you can do the simulation. This is the preparing the eigenstate 0. So you see the phase should be 0. So this is using the simulator. So there's no noise. So of course you get 100% 0, 0 here. The second circuit is for a preparation with a 1, which I use X to apply to qubit 2, right? And all the rest of the circuit are the same. But I should expect that I extract a 1 here and 0 here. Okay, so I should expect 1 here and 0 here. So, and this is indeed what's happening. And the labeling of IBM is, this is qubit 0, qubit 1, and the significant qubit is qubit n. Okay. Any question on the code? I can upload the code to the Blackboard, so you can play with this. So maybe let me switch back to the slide. Okay, and if you want, you can use your account and run on the actual machine. So this is just to show you what I'm going to talk about. So I'm going to talk about all these blue things. You see, I think I'm running out of time. So maybe I'll just leave the slide at this page, and then maybe I end lecture now. Okay, let me know if you have a question.
So if the input state is not an eigenstate, what will phase estimation yield?
Yeah, so that's we're going to talk about that. But the upshot is that it would going to project to eigenstate. Okay, you will read out some phase information that's related to the eigenvalue, and then project that approximately to that eigenstate. Okay, so that's basically this slide. Right, so if your input is not an eigenstate, you read out some phase. If the accuracy is enough, then you approximately read out eigenvalue.
Read out a phase of a random eigenstate.
Yeah, yeah. So you can just expand in the eigenstate basis. Okay, so that's end the lecture here, and I'll see you guys on Wednesday.
See you.
Yeah, see you.